Kia ora, chemistry kiddos. Before we move into our lesson, let's have a look at this NCEA question. We can only do the first half of it now, but hopefully by the end, we can do the second half of it. So let's start with the Lewis diagram for H3, also known as ammonia. All right, the first thing we're going to do is add up valence electrons. So my nitrogen has 5, and my hydrogen has 1. 3 times for a grand total of 8. So don't need these here. I have 8 valence electrons. I'm going to start with nitrogen in the middle and 3 hydrogens all around. Okay. The next thing I'm going to do is spend some of my electrons on single bonds. Each single bond is valued at 2 electrons. So we have 2, 4, 6 electrons that we've spent. So if I've spent 6, I have 2 left over to spend. So what I'm going to do is I'm going to put those 2 here on nitrogen because I can check to make sure everybody has the right number of electrons. Hydrogens max out at 2 electrons, so that single bond has them set, and this one set, and this one set. And nitrogen needs 8 electrons around its central atom. So we have 2, 4, 6, 8 electrons around his central atom, which means he's set. So for me to redraw this so that it looks beautiful without all of my doodles all over it, we're going to have, there we go, there's my ammonia molecule Lewis diagram. Next on our list here is carbon dioxide. If carbon has 4 electrons and oxygen has 6, times 2, that's 12, and 4 is 16 valence electrons to spend. That means we're probably going to be doing either a lot of dots or a lot of lines. The single man goes in the middle, or single element. So carbon is the lonely one here, which means I'm going to put an oxygen on one side and an oxygen on the other side. Okay, now we're going to spend some electrons with bonds. Now, if you remember, I said oxygen loves a double bond. So if we have enough electrons in our pool of electrons, we're going to try and spend probably some double bonds on an oxygen. So even though we know that oxygen is probably going to want some double bonds on it, let's go ahead and work this out the long way. And we'll see and double check to make sure those oxygens really do want their double bonds. If I've spent 4 electrons on those single bonds, that means I have 12 electrons left. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, now let's check to make sure everybody's got 8 around them. Starting with our left oxygen, 2, 4, 6, and the bond makes 8. That's good. And then if we look at our central carbon, 2 bonds is 4, plus 1 lone pair. Well, that's not what we're looking for. Then we've got on our right oxygen, we've got 2 lone pairs, that's 4, and a single bond, that's 6. Still not 8 for that guy. So since our left oxygen has so many, let's take some from our left oxygen, and we're going to take some from our left oxygen, and we're going to put them on our, well, we're going to share them between our oxygen and our central carbon. Okay, so now let's do a double check, make sure everybody's happy. Oxygen on the left, 2 lone pairs, and 2 bonds, that's 8. Carbon in the middle, 1 lone pair, 2 bonds on the left, 1 bond on the right, that's 8. Oxygen on the right, 2 sets of lone pairs, but only 1 single bond, so he's still a bit sad. All right, so what we're going to do is we'll take this, we'll take this lone pair down here, from our carbon, and we're going to go ahead and move it to be a double bond with our oxygen over here. Now, let's see if we've fixed our final oxygen. We've got 2 bonds, that's 4, and 2 lone pairs, that's 4, for a grand total of 8, which means our oxygen is now officially at 8. So, everybody's happy, and we've spent all 16 valence electrons. Alright, our last molecule is nitrogen. So nitrogen has 5 valence electrons times 2 in the molecule for a total of 10 valence electrons. So we can start with 1 nitrogen here and 1 nitrogen here. We'll go ahead and we'll drop a bond in between. I've now spent 2 valence electrons. So I've got 8 more to spend. Let's go. 2, 4, 6, 8 valence electrons. Well, that's clearly uneven and only one of them is happy. So let's see if we can share some around. So if we take this one on top and we put it here as a bond in the middle, now my left guy has 8 and my right guy has changed from 4 to 6. Still not quite up to 8. So what we're going to do is we're going to take some more, highlight the ones here on the bottom, and we'll go ahead and we'll make those another shared bond here in the middle. So now my guy on the left has 2 as a lone pair and 2, 4, 6 in that triple bond for a grand total of 8. And my guy on the right there has 2 as a lone pair and 2, 4, 6 in that triple bond for a total of 8. So now everybody is happy. Now, the name of the shape comes from the valence shell electron pair repulsion theory, also known as VSEPR. So, while you turn to that page, I'm going to turn to mine. All right, valence shell electron pair repulsion theory states that the structure around a given atom is determined by minimizing electron pair repulsions. So, in a bunch of fancy words, it says that 2 similarly charged electrons, which are both negative, want nothing to do with each other and they want to spread as far as possible. So what you see when we see it in action is that the bonding and non-bonding pairs spread as far as possible. Okay, so once we have aligned everything around in our Lewis dot structure, we change it from a 2D structure to a 3D structure. So now we're going to spread out in 3D space. And when we look at these molecules in 3D space, we have something called the electron arrangement and the molecular geometry. So the electron arrangement is the shape of the molecule when you include or with the lone pairs, sometimes referred to as the parent shape. Okay, then we have the molecular geometry, which is the shape of the molecule without the lone pairs. So this is the daughter shape. All right, I slid my page up so that we could have a look at this chart. We're going to fill out this chart, and then I've got a couple of activities where you can explore shapes so that you can look to see how they are. And when I get back, we'll fill out the bottom of this. So as we fill out the chart, we're going to go across, and we're going to talk about each part. So the first one, if I have one central atom that's bonded to one electron region, we would call this electron arrangement linear diatomic. Diatomic meaning two atoms. All right, this has a bond angle, like most lines, 180 degrees. That's a big fat 8. And then our molecular geometry here is going to be linear. The molecular geometry tends to be either more specific or more vague, depending on how your brain kind of interprets it. So I like to draw little pictures so that you can get an idea. My linear diatomic are two atoms bonded together. It could have a single bond, a double bond, a triple bond, it doesn't matter. What we're looking at is two atoms that have a bond between them, okay? Our next one, if I have one central atom and it has two electron regions around it, then we would call this electron arrangement linear. It is also 180 degrees, and its molecular geometry is also linear, where instead of two together, this one has a central atom that has two electron regions around it. Again, a central atom has two electron regions around it. Bond pairs, bonded electron regions. Okay, our next one up that we have here, I have one central atom and three electron regions around it, or regions of electron density, if you want to use the fancy words. We call this one trigonal, like trigonometry, but this one exists very flat, so we say it is planar because it exists all on one plane. The bond angle between each of these is going to be 120 degrees. Sorry, my pencil flipped over to the eraser. All right, so I'm going to go ahead and draw this guy up. I've got my central atom. He has three electron regions that come out of him. So he's a very flat triangle looking shape. Now, out of our three electron regions, I can either have three that are bonded and zero that are not bonded, or I can have two that are bonded and one that is not bonded. Okay? If you can come up with a reason why I can't have any others, hold on to that, maybe write it off to the side, and when I come back, you can tell me, and I would love to discuss that. So let's have a look here. If I have three bond pairs and no lone pairs, I'm going to stay the same shape. I'm going to still call it trigonal planar. As you'll see here, it looks nearly, and by nearly I mean exactly identical. Okay, if I have two bonded pairs and I have one lone pair, then it's going to look a little different. Two bonded pairs, but instead I'm going to have a lone pair up here at the top. I'm going to call this shape bent, because if I don't see the lone pair, because I'm not looking at it, because remember my molecular geometry doesn't look at it, has without the lone pairs, I can cover those up and I look like a bent shape. All right, the last one on our chart here, our abbreviated chart that gets much bigger next year at level 3, Our last one here is if I have one central atom that has 4 electron regions going around it. This shape is tetrahedral. Okay, so I'm going to go ahead and draw this for you. I have one central atom, and I have 2 and 2. So the reason I split them up is because 2 are in the same plane, right? Because we're in 3 dimensions, as our central atom, but then 2 are not. They're going into the paper and out of the paper. So to show that it's going into the paper, I draw an arrow in, and to show that it's coming out of the paper, I draw an arrow out. The arrow in is normally colored in, whereas the arrow out is either empty or sometimes you can see it drawn. Oh, that was a big eraser. Sometimes you can see it drawn as little tick marks to show that it's coming out of the paper. Either one is fine, but you're showing a 3-dimensional structure at this point, which is what we're trying to convey. All right, our bond angle here between each of our tetrahedral atoms is on average 109.5 degrees. So if I continue over to our molecular geometry, if I have no lone pairs, I'm going to look identical to my electron arrangement. So I keep the same name, tetrahedral, and I keep the same shape, a central atom, 2 in the same plane, 1 in, 1 out, and I look like this. All right, the next one, let's say I rip off one of those bonds and I have 2 lone pairs plopped on. Okay, now I only have 3 bonded regions coming off. I'm going to call this one, eraser again, trigonal, which means it's going to look like a triangle, but instead of planar, it's not flat this time. It's going to be trigonal pyramidal, meaning it looks like a pyramid. All right, so he's going to look like this. I've got 3 coming out and my central atom, and this time I've got a lone pair popped on top. Now this guy's a slightly bit different because that lone pair takes up more space than a bonded region. And so since he takes up more space, he's going to squeeze those bonds a little bit closer together. So instead of the 109.5, this guy lives at 107 degrees. Just a wee bit tighter. That's why we say tetrahedral has an average of 109.5. Because sometimes when we add the other bits in, it squeezes it a little bit tighter. All right, our last one here is 2 bonded pairs and 2 lone pairs. I'm going to draw you a picture of it first, and I want you to pause the video and see if you can guess what its molecular geometry is going to be called. So I have my central atom, and I have 2 bonded pairs, okay? And then I'm going to have 2 sets of lone pairs on this one. So I've got 1 set here and 1 set here. But if I don't look at the lone pairs because I'm in the molecular geometry, I know that they're there because they put pressure on the other bonds, but I don't look at them when I draw the shape. Okay, does it look like another shape we've already drawn? If you guessed bent, you guessed correct. Way to go. Now, since in our previous one, our trigonal pyramidal, that extra lone pair squeezed a little bit tighter, what do you think is going to happen when I have 2 lone pairs? It's going to squeeze it even more, just a little tighter. So this one actually operates, eraser again, it really likes that, at 104 degrees. All right, using this chart, I'm going to go back to that first page and I want you to have a go at trying to figure out the 3 shapes at the bottom. and then we'll talk about it when we get back to class. I will leave the video here for a bit for you to have a look at it. You feel free to pause at this point, and remember, when we get back to class, I'll go through these answers.